Welcome back to Demystify Sci. I'm Shiloh.
I'm Anastasia.
Today we're meeting up with an old friend of the podcast, Michael Hughes, who is a postdoctoral researcher and a biochemist at St. Jude's Hospital in Memphis, Tennessee. And Michael has been piecing together a really, really compelling detective story about water's quiet role as a computational structuring entity within the cell. So, traditionally speaking, biologists deal with all of these concepts and chemists as well, but we deal with these concepts like osmotic pressure being regulated or pH being regulated. And the problem is that water is thought to be kind of a bystander in these processes. Furthermore, these processes are extreme abstractions of the first degree and treated as fundamental. So we're really curious what the heck pH actually means. In other words, what is actually happening to the atoms that are involved during this process of pH? What is happening to the water molecules? And how in the world is that doing anything inside of a cell?
And a lot of this is centered on something that we know to be the case, which is that signals can travel faster in liquid water than they can by the transport of molecules themselves. Like if it takes a molecule of water a second to bump through a beaker of water, the signal of the change to that water molecule can pass through 12 orders of magnitude faster than that. And so something must be happening that we don't really have a good sense of when it comes to pH, when it comes to electricity, when it comes to all of these strange water-esque processes that we don't quite understand yet. And that's kind of what Michael's trying to figure out, right?
Yeah, and he has developed this at least very rigorous theoretical framework for understanding how islands of water, which are oriented productively towards one another, can be transmitted across the cell very rapidly at a much greater time scale than, like you said, diffusion and so forth. But the chemistry still plays into the restructuring of these water islands in such a way that you still do have pH dependence and you still do have all of the electrochemistry that we're familiar with, but you have a mechanism by which it can occur very quickly. You also have a really interesting active role for water in the body where it's not just this background bystander. So we're exploring all of this with Michael today, and we run into several of the weird anomalous actions, or let's say several of the points where traditional biological explanations have broken down for us in the past. Very important stuff like how does the mitochondria work? What's up with this proton gradient? Are they really protons? Is the heart doing what we think it's doing? Are there other motive forces by which water can be circulated throughout the body? Really just a ton of interesting, outstanding anomalies that could perhaps be summed up with this structured water explanation that Michael's pursuing.
And it ties into a lot of stuff that's floating around the internet as kind of woo water science, where there's a lot of lore, even among the medical community, about the efficacy of homeopathic treatments, the efficacy of water's memory. And these things on the surface seem dead absurd because you're like, how can it be possible to expose water to a certain kind of chemical and then have that chemical imprint something on the water that even in its absence is still there? Like it defies reason. And yet, what Michael's research seems to be pointing to is that there is some kind of organizational, spatial, and temporal characteristics of water that cannot be explained solely by the presence of organizing molecules. It's almost as if there is a memory to the way that water behaves. That you can take the organizing molecule out and the water will still behave as if it had been in there because this organization is inside of the relationship of the water molecules to each other now. You're shaking your head.
It's just that part still escapes me. But yeah, there are really interesting anecdotes about this. This is obviously really near and dear to me because I did all of my graduate research based around how water might act through structures as a signaling molecule in primitive bacteria. So I'm already sold on the idea that water is doing more than most people give it credit for. And there's a really cool analogy here about water just as the kind of ignored medium of these actions at a distance, which we see playing out in astrophysics and cosmology. And that's really near and dear to our hearts today as well. So this seems to be a bigger problem than just one science. It seems to be something that humans do. We reduce things to the actors that make the most sense to us, and we do that at the expense of what might be a genuine solution to many of the mysteries that remain. So it's a really cool topic for us in general.
If you like what we do on the podcast, consider coming over to patreon.com/demystifysci and joining to give us a couple dollars a month.
Or $1 million a month.
I would not refuse $1 million a month. I really believe that the goal of what we're doing here is to provide a public service where there is a library of ideas that are free for everyone for forever to experience, that don't have cheap ads plastered on them that devalue the experience of, hey, we're gathering here to explore ideas. Like, I don't want to sell you stuff. I don't want to tell you that you should take this course or buy this pill or sign up for this newsletter. I'm like, give a donation to the podcast because you believe that what we're doing is valuable for the world and you want to see more of it. Because if we want to live in a world where things make sense, we need to have an ecosystem of people that are trying to make sense of it. And that, unfortunately, because we have tried to figure out ways to do this without money. Like, we have talked to people that are trying to figure out how to do things without money, and nobody has ever figured out how to do it. And so we're stuck in a position where we have a thing we really care about, which is to take big ideas, the ideas that are going to change the world, that are going to shape the future, to explore them, to bring them to you. But we have to pay for our electric bill, we have to pay for our plants, we have to pay for our lights, we have to pay for our lives, and we need your help to be able to do that so that we don't have to compromise on the principles behind this. So if you can, come over to patreon.com, support us with a couple dollars a month. You get to join us every week for our patron chat, which is also extraordinary because we keep having new people join, young people that are bringing new ideas, listeners who have been with the podcast from the very beginning. We have a couple of people that have been basically coming from the first or second patron chat that we've ever had, which is incredible. So,
and by the way, people sometimes comment down below in YouTube, I wish I could give you some money or whatever. I'm really broke right now. Like, I totally get it. I've been completely broke before, but you can totally share the podcast with somebody, which is, for your circumstances, absolutely as effective, because the way that we grow this project and we bring more people in, and ultimately that leads to us having better and better conversations, is through word of mouth, right? We're not depending on the algorithm or sponsors to push us or anything like that. So just share the podcast, give it a good review, make sure to subscribe, like, do all that stuff. Come participate on Discord or on Facebook. We're hanging out there too for free. So yeah, you can get involved and you can support this project without giving money, especially if you don't have any money.
Twitter, TikTok, Instagram, Discord, Facebook, like you said, we're absolutely everywhere. And we'd really love to see you there. We love to hear your thoughts about the podcast. We love to know what topics we should explore, what other guests we should have. And so there's plenty of ways that you can help support us without spending a single dollar. Those of you who do support us already, we appreciate you enormously. We cannot say thank you enough. And I just hope that we can keep bringing you really excellent conversations for as long as we have life left in this world.
Breath in our lungs,
yeah, absolutely.
Water in our veins.
Absolutely.
Yeah. Anyways, I think you guys are going to love this conversation with Michael. So tell us your thoughts and tell us, where you think this water story is going from here.
The scientific revolution starts now.
Let us see in the dark.
Just to bring everybody up to speed on this, Michael's been on the show before. You all should check that out. I'll put a link. Twice before, yeah. So in at least one of those occasions, we talked about water a bit. And honestly, without re-listening to it, I can't tell you exactly which details we covered, because you and I have talked a bunch about water outside of this podcast too. And
so the last conversation about water was, we titled it, "Is Water the Dark Matter of Biology?" And it was basically this idea that there's something that is inside of biology that's causing things that we can observe, but we don't have a model for what that is. And you basically laid out the first threshold ideas of perhaps it is the water itself.
And it seems like you have been working hard on that journey, that investigation to understand exactly what nebulous role water is playing. I have some quotes written down here. Beyond genetics, water as an electromechanical, computationally competent actuator. So water as an actual organelle, or an organ almost in the body. Water is doing something. And you have, just coming off our conversation over the phone before this podcast, you had this really interesting idea about how the water, the physical bodies of the water, the atoms themselves involved in the water, are reshaping the conductive circuits throughout the cell. And they're doing it in response to things that we would normally think of as acid-base chemistry, but there's actually a structural response. And I think that's the story we're going to be working around right now. So where to begin? I mean, it might be nice if you just lay out the status quo for people right now. Like how do most biologists think about water? And then we can talk about the shortcomings of that perspective, which should lead us into the solutions that you're beginning to provide.
Yeah, absolutely. Thank you for the introduction and getting the ball rolling with what we're trying to do with water here. And so I think that the comparison to like dark matter is really apt on this one. I had a colleague that sat next to me as I was talking, kind of realized like I was describing water as kind of this biochemical space-time, right? If there's space-time in the cosmos that computes gravity, and this kind of dictates how bodies move around each other, then in a sense, water is that space-time that integrates all these different signals from these bodies and kind of gives rise to this force. And there is a force that tends to move things around that water is mediating. So in this sense, I think that there is like this dark matter of the universe, especially in cosmology. As we zoom out from our solar system, suddenly our equations for gravity don't tend to make sense at scale, really big or really small. And similarly, I think that osmotic pressure is kind of this dark matter of water where you can measure the osmotic pressure of a solution. And this is a baseline compared to pure water. So pure water has an osmotic pressure, and then everything you add to that water changes it in some way. And I tend to think of this as kind of like the osmotic pressure being the dark matter of the universe, because we don't really have a mechanism. We're calling it dark matter because it exerts some force, some pull. But it's really just an X in an equation. It's a placeholder to get it to balance, to get our observations to match our theory. And in this sense, I think that osmotic pressure is kind of like that. You get, if you pour sugar into one side of a U pipe and you get this hypertonic solution of water flow, and then at a certain point, the water rises and the forces balance. And this is osmotic pressure, right? It's the placeholder that balances these two sides. But what
it seems like, can I just pause you for just a second? It seems, I want to reinforce that analogy because I think that it's super interesting that the paradigm of dark matter comes in the aftermath of having abandoned the search for mediation of light and gravity, right? So we came up with this mathematical physics approach that we've talked about at length on this show. We'll probably never stop talking about it because it's very productive technologically in some sense to when you're after certain solutions, right? Calculating trajectories, spacecraft, whatever it is, right? Very productive. But at the same time, it kind of closes the book on asking questions that might further your overall general picture of the phenomenon. And the same thing seems to have been the case with our approach to cell biology, which is that we have these proteins, they're doing things to each other. And in the background is, there's water, right? There's something there, there's space-time there, whatever it is. But we've closed ourselves off perhaps in this tradition to considering the active role that water is playing in mediating phenomena. I know you already said that, I'm just reinforcing it, yeah.
No, I think that's very right. And when you talk about this active role in mediating this is what was so exciting to me, because I came at this problem as a protein structure biologist. So doing X-ray crystallography and looking at how these protein enzymes that are these machines doing chemical reactions in sequential order, or ATP synthetase, this rotor that is making our energy source, that it kind of gets rid of the magic or the black box that just placeholder, because now as opposed to having this placeholder of like a block in a cartoon in a textbook that does this chemical reaction, I can see where the atoms are moving around. And in the very same sense, we can play this game with water because our technology's gotten so good now. We can do such fast like pulses of light. You can start to do pulses of light and measure, faster than the water can like let go of the light you just threw on it. And when you get to do these things down at through like femtosecond time scale and picosecond and attosecond, you get to start to see how the electrons are effectively moving around or shared at the water molecule. And so you get to see how osmotic pressure begins to become a manifestation of changes in where the electrons are at the atomic level. So it gives mechanism. So I came at this from a really like interesting mechanistic kind of mindset. Yeah.
If I can interrupt you, can we really, in some brief way, lay out what's weird about osmotic pressure? Because in other conversations, you've mentioned that when you came across osmotic pressure, you realized that people didn't really understand it. And I think
It seems like it's like the warped space-time in this analogy. Or it's
maybe,
the space-time that's being warped or something like that. It's this abstraction that's taken as the fundamental mediator.
yeah, I guess I don't know how stupid I am about it yet. And so
Yeah,
explain to me just how little we actually understand it. Because it's always seemed like a given of, well, I don't know, you have different concentrations of things and they move to places of lower concentration. And I'm kind of like, well, that makes a lot of
right.
sense.
Exactly. Places, things in higher concentrations move to places with lower concentrations. This is like the base concept of that we would like keep in our back pocket to describe osmotic pressure. But the issue is that when you dive into it, you start to see these ways that that's kind of like cheated. You can maybe have some chemicals where water seems to flow up its concentration gradient because the chemical difference between the two acts on it in a weird way, so that you get water trying to like flow potentially in opposite ways. And so
Are we
osmotic
talking
pressure,
about polymers here or like things that
yeah,
really,
this is
okay, so things that are really
is
heavily
it,
hydrated that are really absorbing water tend to screw with its osmotic capabilities.
yeah, yeah. And where
Damn,
this
sounds like
goes
you
is
know a
that
lot about this all of a sudden.
Well, I've spent enough time with Shiloh talking about polymers that I can be like things that are hydrated, right? Because polymers basically are these long chain molecules that, when dry, can be a powder, and then when you put them into water, they expand and attract a lot of molecules to the chain.
The gel
The
phase.
see,
that's right. The gel phase. And so like a lot of times osmotic pressure, you measure it by having you dump a salt phosphate into, or even just like ATP, a nucleic acid alone, into water. You can measure a deviation of the osmotic pressure, how this liquid now interacts with the world around. Basically, the vapor pressure, how easy it is to get water to leave or enter into that solution. Now, when you staple all of those like monomer salts together into a polymer, you massively change a lot of the properties in a nonlinear way. And so now suddenly, if you're using this equation to model osmotic pressure, when you turn it into a polymer, you start getting like nonlinear effects, right? You start to see that the solution you're measuring isn't behaving as your equation accounts for. And it seems like polymerization is a really big way that we get to like get these crazy weird effects. And as your body just so happens to be filled with polymers everywhere, whether it's protein or DNA or RNA, right? These are all polymers. And so it's just right in that range where weird things happen, right?
and so basically the takeaway here is that if you have a really simple system where you have the experiment that most people probably did in high school chemistry
Yeah.
or high school biology, where you have this semi-permeable membrane and you add sugar on one side to pure water, and then you look to see where the water level changes to, that's a situation that is incredibly far removed to the conditions that are inside the human body, where, like you said, everything is. We imagine the cell as being a bag full of water. Like introductory biology textbooks tend to draw it as the cytoplasm is the fluid in which things happen. But that couldn't be farther from the truth, because what it really is it's this incredibly structured polymer protein filled space. And so the idea of osmotic pressure being the thing that operates inside of a biological system is therefore really superficial and highly oversimplified. Is that kind of what you're driving at?
I think that there's a world where it's highly oversimplified because, again, we're just going over how. I mean, I didn't have a great conception of osmotic pressure going into this until I really dove into it, right? Like, where does it come from? And so the power here is in how understanding where osmotic pressure comes from helps us understand where life may like to live or may not like to live. Because there's certain environments that life tends to hone to, and when you get out of these environments, this manifests as like cancer, right? So if a cell isn't doing the metabolically correct thing, like turning energy over in the correct lockstep with the other tissue around it, starts doing its own thing. Uh, this is kind of a manifestation of like this uh, phase transition. Or so remember where you just left off on.
Well, I was basically trying to connect this idea that there's something weird about osmotic pressure, where we established that
Right.
osmotic pressure in a test tube is one thing, osmotic pressure in context of polymers is weird because you watch water, instead of traveling up its concentration or down the concentration gradient, it travels in the opposite direction. And then I connected it to cells on the level
I think it's
of-
important to, like I said originally, that we set the stage for how people think about osmotic pressure in the cell to begin
Yeah.
with. Like, what's the traditional
And
approach to this?
Well,
what I kind of want to get at is like this idea of scale. Based on what Anastasia was like leading off was is that if I dissolve a salt into a beaker, I can get the osmotic pressure of that solution. Now this gets more interesting when I dissolve or actually just place a polymer like Naphthion from Jared Pollock's like Easy Water story into water, and so I can measure the osmotic pressure of that beaker with Naphthion and water in it, and I'll get like a measurement. But if I zoom in, I can see that the osmotic pressure closer to the polymer is like hundreds of thousands of times greater, right? Like incredibly, like way bigger. So as you zoom in, you lose that homogeneous measurement, right? So I can do a measurement of osmotic pressure that a cell is in. And in fact, there's papers published like one in 2017 where if a stem cell is trying to differentiate, so a stem cell is trying to turn into, let's say in this case, a fat cell or a bone cell, the osmotic pressure of the solution that you keep it in will influence which fate it decides to go to, right? Because in your bone, there's much less free water and it's a much stiffer substrate to grow on. So now I don't need to throw chemicals on to get my stem cell to decide where to go. I can actually kind of just change the availability of water. So just by zooming out this big scale, right, large zoomed out scale knob of osmotic pressure, I can get incredible difference of behavior at the very micro level. Right. And so osmotic pressure does like translate through scale really interestingly through biology. That measurement, that one number can give me a lot of control. But then when I zoom in, right, it breaks down into these separate strata where you can see closer to the gel, it's different and that's balanced by something farther away. And then we start to go into like the cell and how complicated this like lattice looks, of water environments.
Now, how does that picture differ from the traditional conception?
I think that it doesn't differ too much from it. Is people kind of know about this and know it matters, but I think that in my experience of being a cell biologist or going through school and learning about genetics is kind of like these reaction pathways. And so you have this enzyme and it does this thing in this cascade. And so you get cycles, you get some interesting shapes in how material metabolites and information moves through the cell, but there's no mechanism of that. So it doesn't give you great predictive power, right? If I see that this cancer cell line upregulates this thing and downregulates this other thing, that's like interesting for chemical pathways. I can try and upregulate something opposite, but it's kind of unreliable. It's so tricky to get this to go from like an idea into a patient, right? It's so hard to turn these to get these cures to diseases we're looking for. And even my own personal experience of like amyloid diseases and Alzheimer's disease and Parkinson's and ALS, we still don't have a good idea of really what's going wrong in the first place. So I think that the contribution here is more of a framework to interpret what this stuff like actually means. So if we're doing hypothesis testing, we also have access to, we can upregulate or downregulate this enzyme or turn on or off this pathway in the cell. But this is also going to change how like water or nutrients or energy flows through the system. And it's going to be very tightly related to osmotic pressure, the balance that like it must keep a balance of osmotic pressure inside and outside. And how you keep that balance, now you're talking about things like pH changes or changing your membrane potential, taking in nutrients or not taking them in. So if you're in a cancer environment, you might just not be able to do the chemical reactions you need to move some like nutrients through the cell that might otherwise be available. And all of this kind of framework of thinking about it becomes open with understanding like the manifestation of osmotic pressure and how it limits how the cell can move information through the system. But it wouldn't be apparent if you're just looking at genetic pathways from above.
Okay, so at the heart of this is this concept of osmotic pressure. And this might be really stupid, but osmotic pressure, as I understand it, is when water is moving towards a region of high solute concentration. Why does it do that? Like, why does the water move? Like, what gives it that motive? What motivates it? Like, what? I mean, I understand in principle, I understand it as a description of what is apparent, but in terms of the motion of these bodies, like, what is the force, like, arising from? How does this happen?
And I guess the question, to elaborate that a tiny bit, is it the water that's moving, or is it the solutes that are moving? So if you have, let's say you have a cube of salt, a salt crystal in the corner of a beaker.
I can understand the solute crystals moving by diffusion and just thermally exploring their environment and stuff, and maybe that's what's happening to the water too, but like the pressure of the water in motion, I assume, is what we mean by osmotic pressure. So what is causing that motion?
Yeah.
This is probably really stupid. My advisor is cringing if he's listening to this.
No, I think that there's maybe even like a few ways I could answer that question and what's causing this motion. So there's a few like weird things to paint this picture. The first one is, and kind of this like U-pipe experiment that I was talking about. You dump solute on one side, and you have this semi-permeable membrane where water can go through, but the molecules can't. You'll notice that membrane will never bulge. But if you put like a plunger on one side and push down, it's going to bulge and break. But you can't like put chemicals in to do that. So osmotic pressure is different than pressure on some level because it's only felt at the level of like the molecule, at the level of the water molecule at that pore. So that's kind of curious because also these pores are all over in our body, whether ATP synthetase is a pore that's like gating osmotic pressure, like these different environments, or the nucleus versus the cytoplasm, or inside the cell versus outside. So this kind of thing like shows up a lot. So
is that just because the pores are permeable to water, so it doesn't bulge?
Yeah. So I guess what I'm trying to illustrate is that where osmotic pressure, like where you will find it down, I boil it down to is like how the oxygen and the hydrogen in an OH bond of water share electrons between them. That's where this will like end up at. And so like a weird way to imagine this is I like to think of acid and base as like opposite distortions, right? So there's like charges are kind of like opposite distortions of space-time. And that's one way to think of each other, as they like to like attract each other and cancel out. And that kind of changes, if you have angular momentum spinning like one way, something spinning the other, kind of like cancel out. And so in a way, every time you distort, you put a chemical into water, it's going to have distortion in one way or the other. It's either going to look like when I'm talking about the sharing of electrons and oxygen between oxygen and hydrogen, one of the distortions will pull electron density towards the hydrogen and the other one will push it towards the oxygen. And this is in essence what acid and base is kind of biasing the average electrons in that bond one way or another. And when you do that, you actually change how water likes to move around. So water free in solution, just nothing pH 7, which is theoretically super hard to do. But if I am a water molecule and I'm looking to change hydrogen bonding partners to like one person on my left or like a water molecule on my right, it's about just a coin toss. In water, it's pretty clear like which one I do. But now if I'm water and I have like a glass on one side and free water to solution on my other side, it's no longer the same balance because water wants to find its lowest energy level, as everything does, its most stable place. And it turns out that all the water molecules interacting with the glass surface their motions are kind of arrested because they don't have the same space to explore. So they can't diffuse from left and right. There's literally a glass getting in the way of something diffusing from the other way. So suddenly it's like a possibility space to explore for diffusing and motion is completely like truncated by having that glass wall there. But if you zoom in, this is also like a protein right on the surface, just the macromolecule or the polymer itself. The water can't diffuse from inside the polymer out. It has to diffuse from outside the polymer in. So
And
this
what is
is
the
where this,
effect
like,
on the osmotic pressure as a result of this?
because of this, water wants to kind of flow down the osmotic pressure gradient. So the polymer or the glass makes strong osmotic pressure nearby, and the water wants to flow into it. But at a certain point, it can't compress it anymore, and you get equilibrium, right? So it does want to flow like down towards that area, and you get equilibrium when that's equalized. And in the glass, that looks like the meniscus around the glass, right? Like that water that's climbing the side of your glass is in some structured order that gets to fight gravity a little bit more than the stuff in the center. And this is a manifestation of osmotic pressure in a sense. And so osmotic pressure eventually becomes a hindrance of water motions because of the things around get in the way of that. So hindrance of water motions mean that if like I have a sugar molecule or fat molecule in between waters, it can't move through that molecule, it has to move around it. And you get weird geometric effects with that. And then the second thing is the composition of that molecule. And that's where the sharing of the electrons comes in. And this is where pH comes in. So if you pull the electrons towards oxygen or push them towards hydrogen in water, that changes how it likes to move. And that's the one extra thing that I think I put on top of osmotic pressure that only recent like experimental science has kind of unveiled these really tiny motions recently.
So let me make sure I understand the answer to the question of how the water moves during osmotic pressure or solute addition in the U experiment. Is it something like transpiration where the waters are getting adsorbed to these surfaces and then pulling like neighbors from across the tube over?
That's effectively how it is felt to the water molecule, yes. And if you look into it uh, at like a really high level, that's going to look like cooperation of electron sharing and hydrogen bonding network that's going to be able to mediate that signal to waters that are far away. Right?
So to give a visual picture for somebody who hasn't done this experiment, you have the U-shaped tube, you have a membrane at the bottom of the tube that's only permeable to water, and you add sugar to one side, and the water on the sugar side, the level of the water, you start out with the level in the U-tube being equivalent. As you add the sugar on one side, that side's water level goes up. And
Right. And
we're saying that the reason that water level goes up is because as the molecules of water hydrate the sugars, they pull the other molecules of water through this porous substance in order to be able to also organize them. Like the organizing principle of the sugar is what pulls the water molecule through the membrane in order to create a higher volume on the sugar side. Is that what we're saying?
That's the
I
YouTube
think that's
experiment.
Yeah, I think that's close. And one thing I would modify is that the the water is just bouncing around by Brownian motion, and after doing a million coin flips, because it's slightly more favorable to end up on the side with a lot of solute, it's going to end up there. But over like if you're just watching it for a few seconds, it's going to look super wild. It's only when you zoom way out that you get to see this mass transport over a big scale. Right. And so the water isn't necessarily just like honing in, it's doing a bunch, it's just, navigating with a bias now,
Well,
and
because
it's feeling something.
the amounts the time scale of the motion of an individual molecule of water is several orders of magnitude faster than the time scale that it takes the U-tube to fill up on the right side. I know.
Every time you say YouTube, it just cracks me up. So
Yeah, it's true. And what's cool and weird about this is that the osmotic pressure change is felt much faster than water diffusion is felt. So the difference that's going to drive this mass transport happens much faster than molecules actually physically running into each other.
it's like a
This case, and
tension.
this is exactly, it is like a tension. Where so what's got water's attention, and if it's paying attention to salt, it's not paying attention to hydrophobics probably.
Oh, I was saying tension, like Yeah, like it's like a
Oh,
like a stiffness almost. I don't know.
But I
yeah.
think that the
So,
tension and
Yeah,
attention
yeah, yeah,
play kind of
yeah.
a similar
yeah,
role
yeah.
here, right?
It's true. And people talk about water as like a tensegrity system or your body as a tensegrity system, right? And so tensegrity being a way where like suspend something so everything is under tension, but you still get to like stack up, right? And the cool thing about this is that like, you know, if I have Legos without any tension, if I pull the top brick off, I just pull it off. But Legos with tension, I get to like pull the whole thing up, right? And so if I pull on your head, it doesn't just like come up off, right? Your whole body comes with it. So by definition, your body is this huge like tensegrity system where you're kind of like bootstrapping this like way to the top, and water is a great tool for doing this because of its like strong one like attraction to itself, right? Water is
And
really attracted.
it seems like
Yeah.
it dances around this other interesting paradigm shift that we're watching unfold in fundamental physics, which is electrical conductivity in general, as being in general faster than, you know, the motion of individual electrons, whatever those are, right? So you have some other process emerging which allows
Mm.
action at a distance through this chain, right? So you had that Jude model for a long time that was kind of treating it like a chain. It's not quite like that.
Explain to people what that is. If they
The
don't
Drude
know.
model is essentially like yanking on a chain at one side, from what I understand, or pushing, you know, like one of those dog collar chains or something like that, where you have, or like the what is it called? Newton's cradle. Cat's cradle. So that's a
That's
rock
the
song.
string game that children
Oh
play.
yeah, it's the game with the string. Newton's cradle is this immediate transport of inertia. It's not really immediate, but it is very fast. So something like that, which is emerging
For electrical
for
current
electrical
transduction. So
conductivity.
basically, it's like solving the Drude model is important because for a long time everybody's conceived of current as being the flow of electrons, and so when you flip the switch, you get this river of little bowling balls that are suddenly tearing through the wire. And then when you look at actual drift speed of electrons in a wire, they travel slower than a garden snail. They're just incredibly reticent to actually move. And this model that Shiloh's talking about, the Drude model, is suggesting that what matters is not the motion of the individual electron. What matters is the transmission of this impulse, as if with Newton's cradle, where the minute that you close the switch, you've pushed the entire chain forward, and it's that motion that transmits instantaneously, despite the fact that the electrons themselves move really slowly. But you were Shiloh, trying to get
It
this to the
just seems
point
like
of,
we're looking at. Well, I don't want to give away your punchline, but it seems like what you're talking about is the organization of of collective conductive networks and so forth. Like you're actually talking about changing structurally the organization of this electric circuit through the addition of solutes, polymer chemistry, acid bases. I feel like that's what we're dancing around.
where it's like what moves is not the molecule. What moves is the organization of the
Yes,
molecules.
which allows new conductive possibilities and so forth.
That's exactly and how I imagine it too. And if this is perfect with waves, I mean, if I imagine I'm like at the beach and a wave hits me, right? The water molecules themselves are barely moving as the tide goes, right? And out slowly, but they go up and down quickly, right? The wave transmits through it. It's the medium of that. And in this way, I think that this lines up really nicely with the like how physics is dealing with the Drude model as well in water. And so I feel like Veritasium had a really good YouTube series on kind of electricity and the misconceptions. And I think that osmotic pressure will look really similar to something like that if someone dives into it. And what is really curious of how fast this like transmission is, and that's kind of what I'm getting at, is what's curious about osmotic pressure is it's transmitted faster than these. It has all these same principles and same ideas. And what it becomes is like waves of organized information seeming to be transmitted ahead of the actual like arrival of the molecules themselves. And so then water becomes this really interesting medium that can like integrate all of this so quickly because water motions change. It changes its hydrogen bond on the scale like picosecond or less than a picosecond. Nanoseconds is what it will take for a protein to diffuse. So water is moving thousands and thousands of times faster than the big molecules like around it. So you get to, move things and information through your body much more rapidly than we'd expect if we just want to diagram like the fusion of these molecules getting there as the signal.
Is it traditional to just consider the fusion kinetics and so forth? Like, I'm trying to understand how this departs from the classical understanding of the situation.
Fusion kinetics?
What,
Diffusion kinetics?
did I say fusion? Diffusion.
Okay,
Yeah.
okay. I wasn't sure if there was something I was supposed to say. Okay.
Yeah, it's become an odd one for me because now that I've like dove in so far into water, when I first was really interested in, water is like quantum physics. It's where we like brush all the weirdness that we can't explain quite yet, and like go on about our days. And so the odd like unveiling of this is just how extraordinary like mechanistic water is. So if we're talking about like beating physics, right? Like I know water doesn't do that in a sense, right? There's like these interesting things it's clearly doing, but as I peel back the layers, it becomes more and more mechanical of how this could it was like actually transmitted. So when most experimentalists, I believe in their papers, they'll come across a series of equations for modeling what this might be, what this transmission diffusion of chemicals like in a neuron, right? Let's use the example of a transmission signal in a neuron. And so you have equations for diffusion of these things, and you can try and get them to like fit. And if they don't quite fit reasonably, then you start to invoke odd mechanisms that must be going faster or changing it in some way. And so then a lot of times the paper will be alluding to hey, we measure this thing that is like not behaving the lines within the bounds of the lines we expect. So it probably is demonstrating that something unexpected is happening, and this is probably what that unexpectedness looks like. So we're never like beating physics here. We're just slowly unveiling how our models like didn't quite capture it, and then trying to do the refinements. And at a certain point, we're just going to have exhaustive like textbooks for osmotic pressure coefficients under temperature and pressure, and this gets like what does one do with this? So I think that it's really curious then to try and like build up from this understanding to biology like harnesses this in very particular like routes. I think that the information is just so all over the place. You can measure in any direction. It's how we integrate this knowledge to like hypothesis build. Yeah.
So from where we're sitting and what we've done so far, it seems like the next logical place to go is to say, okay, there's something really interesting about the way that water behaves, where it's able to respond to some kind of chemical, physiochemical signal much faster than it can actually move. Like it senses things at a distance. Is that, are we?
Which gives it an interesting computational power.
Yes. And so if we then go to the question of what are the weird things that this lets us do in biology, we can start to explore in context of a whole field, which is all about the weird behavior of water that comes at it not from this very, very technical sense, but this is going to sound crazy, but the memory of water, homeopathy,
Yeah.
the idea that you can treat water by setting it out under the light of the full moon and then water your plants with it. And
Several people just unsubscribed.
But I think that this is what's so interesting is that you have this kind of folky wisdom that gets passed along between people. And if we take the idea that indigenous myths contain within them a grain of truth and science, then we also have to consider that somebody who's pouring 10,000x homeopathic dilutions of arnica on themselves or whatever is doing something that's informed by some seeds that could grow a pearl. And so I'm like, okay.
Enormous levels of dilution are detectable in the olfactory world, right? You can like dilute a drop of certain substances in a swimming pool and people can smell it still, which is fascinating. All right, so I mean, one way to attack this though, I know we told you not to bring any pictures, but it might be cool, and we can edit this out, but you had a couple of examples of the restructuring of water in some of these very simple situations like acid-base chemistry and so forth, and it might help everybody to show some of those pictures if we're going to go through these processes one by one and see how they're different or how they're affected by this restructuring?
I agree completely. I'm happy to bring up some of the things I showed you earlier. We can work through. I also am curious if I had to respond to Anastasia's about like the curiosity parts. I also was very curious too in diving into this of you know being a professional scientist and coming through the training that I did. It seems really hard to understand some of these odd things like the homeopathic memory of water being effective, or the the memory. And I think a Russian scientist, big story, Nobel Prize winner, said that he was able to like shine light on a tube of water that encoded information for the HIV genome, and it like reassembled in another test tube with just the raw DNA components. And so that light, so there's some very, very, like in a sense, like far-fetched claims around here. And what's curious is like the grain of truth at the bottom of it. And what I mean by the grain of truth at the bottom is that I'm not here to refute these grand claims. It's just beyond me. But there's some really interesting water behavior that I do know about that like alludes to some of these things. So one of them for like the memory of water, and I learned about a bunch of these from my mentor, Dr. Eisenberg, who spent a lot of time studying water as well. But he would share these things where I was doing amyloid protein studies, which is when you form. The idea is that when you form this nucleated protein fiber, it acts like a prion or a primer, this infectious agent, where now all proteins with the same sequence will now add to this fiber, and you have an amyloid fiber. And this is seeding or protein seeding. But
Like
also
mad
when
cow
you
disease.
exactly, this is mad cow disease. And so if you eat this protein seed, then you can turn your body's like prion protein into these fibers. So there's this sense of this like memory of this thing that you can inherit, and it looks like this nucleated seed. So you can take some ice structures, and first of all, ice doesn't ice at freezing at 0 degrees Celsius. Pure water, you at very small bubbles like nanoliters, you can cool it to like negative 100 or 150 Celsius before it'll freeze. And what this starts to show us is that ice freezing is really important on this nucleation step. If you have really small volumes of water, it's very possible that it just never samples that organization of water molecules that actually leads to an ice crystal forming. And furthermore with this, you can take ice and you can freeze it into certain phases. So we have like 10 or more phases of ice. You can do weird experiments like freeze water to the correct temperature and pressure, and it'll go to like phase 4, and it'll never get to like phase 5. But if you make phase 5 through a roundabout way and then melt it and then refreeze so that you normally hit phase 4, it'll go to phase 5 instead, because it has this seed or this leftover memory. It's not completely dissolved this past like ice crystal memory. And so this is very reliable. You can do this. This is published, right? I'm not throwing anything crazy at you, but in it is a seed of this like weirdness. But again, there's this mechanicalness to it. It's like, I know about these seeds. I know about these things. There's another one that's really curious called the autofixate. Oh, yeah, go ahead.
Well, I think that it's worth pausing on this to absorb how weird this is. The idea that you can have a conformation of a substance, remove the conformation entirely because it's a temperature dependent process. And so if you right, so it's like if you have this ice 5 or whatever, and then you re-liquefy, remove it from the phase, and then you return it back to its original phase, the fact that it can go back to that conformation, to that organization, instead of the shape that it would go to previously, is astounding. Like, this reminds me of, I don't know if you've heard about this, but there's this thing of disappearing polymorphs.
In like crystals or water in particular?
In crystals and the production of substances. I can look this up really quick.
Production of substances makes you sound like you have a meth lab somewhere.
Yeah,
but I've heard a few stories of this, yeah.
It's related to meth labby stuff, I guess, in the sense of organic chemistry or chemical synthesis. There are substances that can have only been produced once in the entire history of organic chemistry synthesis, and they think that it's because once they get produced, there's something in the air that remains forever that prevents synthesis from happening again. Like the products of a single synthesis make it so that the synthesis can never happen again, not just in that laboratory, but literally in the entire world, and nobody knows how this happens.
I've heard stories, but I don't know much enough about like the specifics. But this is very like reminiscent. I think that at a certain point, that's why like I felt so obligated to share some of these odd water stories from what you share with this kind of like mystic element of like that we get to throw into the water, hiding all this crazy behavior, is because there is really legitimate information we're aware of that makes this very reasonable to ponder. Yeah.
Yeah, so I pulled up the disappearing polymorphs Wikipedia page. In material science, a disappearing polymorph is a form of a crystal structure that is suddenly unable to be produced, instead transforming into a different crystal structure with the same chemical composition during nucleation. And so basically, the original polymorph just disappears from the universe after it's been made once, and they can never make it again.
Fascinating.
And sometimes, like I said, it's not just in a single laboratory, it's literally like everywhere in the world.
Sounds like people.
Yeah.
Sounds like people?
Yeah, I mean, you never get the same
Yeah.
person twice.
Yeah,
I
but
am
Jupiter is
unused
never
to
overhead in the
think-
same place twice
I
either.
am unused to thinking about chemistry in the same lens though, so that's really interesting. And so, but
You
this
think you're
water
not a
stuff,
chemical reaction?
so, like, it seems crazy that a purified synthesis reaction could follow such principles. So you're
It's
right.
alive. Yeah,
Something weird is happening.
that's really weird. Yeah, by
Something
the
weird
way,
is happening. Yeah.
I wanted to ask you, what in the world do people mean when they say that water freezes at 0 degrees?
What do you
I think it's a great
I don't understand.
question.
Well, you just said that it doesn't always freeze at 0 degrees. I mean, is
Yeah,
this
so-
related to supercriticality? Like,
Water is very curious. So, from my understanding, this stuff I haven't checked a ton. So, but I think that most of it's like reasonable in that if you have an environment of like 99% humidity or like going to 100% humidity, at a certain point, you can just put water into the atmosphere and it'll just effectively turn into a glass of water. At some point, it'll just do that. And so it'll like never nucleate and fall out, is what I'm saying. And we see this in chemistry all the time where you can super freeze water and in a plastic water bottle or really clean glass in your freezer, pull it out, it'll be liquid and then flick it, right? And then it'll freeze. Right, you can do this with super critical solutions of sugar, where you cool it and then it crystallizes out. So 0 degrees seems to be under the correct conditions just on average, right? Like when this happens. But we know for sure you can repeat this for yourself. You can get water that's negative 20 degrees and not frozen, and then try and handle it, and then it'll freeze right there. But
This also works
yeah.
for boiling too. Like I went to this Renewal of Science conference, and there was Ha-Sok Chang, who's the history of science professor at Cambridge, and he did a bunch of experiments on the boiling temperature of water, and he showed that by varying the vessel size and shape, he could get water to go to like 110 degrees Celsius without it boiling.
It's perfect. And so what's so incredible about these metaphors of water with this like seeding and criticality is that in biochemistry as like an amyloid researcher with these fibers that nucleate and drop out of solution we see that most proteins on the face of the planet like have a part of them that can probably do this process, become a prion-like protein. What's like fascinating, and so your cell's always at this super saturated protein concentration, filled with these proteins just waiting to turn into amyloid disease. And what's magnificent is it just really rarely happens on a day-to-day basis of being a human, right? Most people go 75 years without like this really being an issue. And that's quite remarkable because in the test tube and lab, I can't keep my proteins from doing this, but in the cell, you do it all the time, right? So there's something really unique about when we're doing experiments in the lab, I'm always getting amyloid fibers, but when I'm doing them in the cell, I'm never getting amyloid fibers. To try so hard, you have to really genetically mess up a mouse for it to start displaying even the faintest of like amyloid pathology. And so there's these huge things that we're kind of like missing that our bodies operate in this just about to nucleate and drop out environment for our whole lives, but only rarely does that seem to show up. And so what are we missing in that crossover?
We have established this idea that there's a strange memory of water. There's a memory of substances. There's the ability to respond to environments faster than should be possible based off of pure transport dynamics. And so we have all of these different pieces that are important inside the cell, which is one is pH, which is the condition under which proteins are satisfied, basically, I think is the easiest way for me to visualize
And
it.
this is kind of a master control switch, right, in biology, and then it's become like a real interesting thing in the health world, right? Like,
Yeah,
you
like
gotta get your pH
alkalinized
right.
water.
Yeah.
Yeah.
So it's worth unpacking it.
So like pH is really important in biological systems because if you and fundamentally it's an electrical phenomenon and it's also a water phenomenon, and so if you have proteins that are in the wrong pH, they'll denature. The same way that if you I'm hard pressed to think of an example. Like milk will curdle if you add lemon juice to it.
If you chug a cup of
Right.
bleach, your throat will denature.
Curdle.
Is
That's
that
true.
is that what bleach does? I just thought it was just
true.
breaking the cells open. I mean, I don't know. I don't know about that one.
If you eat too much pineapple, it'll the proteases cut up and digest your mouth some. That's why your tongue gets sore with tons of pineapple.
I
Whoa.
didn't know
It's fun.
that. Okay, so
It's
we
good for
have but that's not pH. This is like
No,
proteases. I mean, I think bleach is just chemical rupture. I think sodium hydroxide just dissolves membranes.
I mean, it's a strong base, right? It's got
Yeah, okay. All right. I'll take that. So like lemon juice, bleach, all of these things are really destructive because they screw with proteins. The proteins break open. They don't like tear the proteins apart. They unfold the proteins. And the
That's
folding of the
exactly right.
proteins is really important for stability. Then we also
Yeah.
have in biology that literally electrical transduction is really important. And I remember you talked about this too when we were talking earlier, where the presence of sodium versus potassium versus magnesium versus calcium also strongly affects the way that water moves and its organization. And so was there more than that?
No, that's quite a that covers it fairly nicely. As in you can get the whole thing packaged in that story. And yeah, I really like the folding and unfolding part, right? Like when you put acid into milk and it curdles, or something, right? Like milk, if you zoom in, it's just all these droplets of different types. You have protein, you have fats, you have protein stabilizing the fats, and it's this nice homogeneous liquid. But then when you dump lemon juice in it, it becomes goopy, right? The proteins, they change their conformation so they can't hold everything nicely in a homogeneous solution. So this is in essence like a phase transition, as any other. And what's cool about this for me is an amyloid, right? This is what happens when you change the pH and you denature your protein. It unfolds. Now it reveals these parts of it that can form these amyloid fibers or these prion-like things. So when you exist the most of your life in this state where you're not getting these diseases, right? There's something really cool where if you are in a healthy cell, like a muscle cell, lots of protein everywhere, and you want to unfold, if you unfold, you increase your surface area. And when you expose new surface area, you have to put water on that. You have to hydrate it, right? And so in a sense, your cell can stay like what we call supersaturated, more proteins than it can hold safely, because as long as you say that concentrated, it's so energetically expensive to fall apart. You can't put water on those new like areas that are exposed. But when you do a phase transition, like by adding acid or base, you change the structure of the water so that the pressure that this protein is feeling to stay like curled up in this ball changes. And so it's like a bubble with surface tension, right? When you change the pH, it now becomes like the same structure as your bubble surface. So there's no divider, right? And so you fall apart when you start to make that water structure the same as your surface tension bubble would be. So as you're changing the pH, that's what can unfold a protein in essence.
Okay, so let's do the same thing for pH that we've done for osmotic pressure, which is this is the way that people normally think about pH. This is the missing pieces from that, and this is how this new perspective lets us think about pH.
And so pH is effectively like charge or voltage stored in water, right? In liquid. So when we're measuring with the pH meter, right? We're measuring the electrical potential for that solution to do work. And the only way that electric potentials do work is if there's a relative like difference, right? Something can flow down or like climb up, right? Things want to flow down. So you need some place for something to go if you want to do work. So when you put like a pH probe into your solution to measure, the pH probe actually leaks a salt solution into your measuring solution. And so you're measuring the electronic work done by moving that salt solution into your solution or something equivalent to this. So what I am then
It's amazing that I made it through 15 years of working in laboratories using pH meters with no understanding of how they work.
Me neither. Me too. I mean, also, until recently, I had no idea what I'm measuring. And so you measure a voltage, and then you convert this voltage into equivalent like hydrogen charges, and you can do corrections of various sorts, right? And so then you end up with your pH, the log hydrogen. But really, what you've measured in its raw form is electrical potential as measured by voltage between two aqueous solutions, and the ability to like work or transport of an ion.
Man, we could just stop right there. My brain is absolutely blown. That's amazing. I love that.
I mean, I think that I knew that pH meters had special permeable, because the way that a pH meter looks when you're working in a laboratory is you basically have, and I remember this, that you would always have to refill
the
the
little jar
capsule.
thingy that it sits in?
That's right.
Not just that it sits in, right? It sits in a jar which prevents the glass from drying out, but also
Right.
is filled with a salt solution.
Like
And
inside of the probe.
Do you
inside of the
remember
probe.
what
And
it
so
is?
the
Do you remember the salt solution?
God, is sodium of some kind. I don't really like silver.
Silver or potassium
Nitrate?
chloride are
Chloride.
often so like 3 to 4 molars potassium chloride is like a common one that I'll use. But there are some other ones as well, like silver.
Yeah, I think that for me it was usually potassium chloride. And so you basically would have a bottle of the solution sitting nearby, and you would have to periodically, when you were done using the probe, refill it because there's a fill level of the probe. And I kind of always assumed that the reason that it disappeared was because there was a hole in the probe and that it would just evaporate. But now that you're
That's very true.
talking, it's like it could also just be leaving.
Yeah, you're using that to do work to measure how much is leaving. You can measure that charge going through, I think. All
That's
right.
fascinating.
Something around similar to that system is what you're physically measuring, right? So I asked very pointedly if you remember what you're using, because potassium chloride is used, in my opinion, it seems for a very specific reason, and this is because when you dissolve potassium chloride in water, its pH stays very close to 7, right? But now, if you dissolve sodium chloride in water, it'll be slightly acidic. And if you dissolve sodium fluoride in water, it's going to be quite basic very quickly. So what I'm trying to unveil here is that we actually use specifically sodium chloride because the balance of the positive ion and the chlorine ion makes it about pH 7 neutral. So there's like no potassium.
You said
Uh,
sodium. Just
so thank you. Yes, that's right. And this matters here. Potassium is and chloride, they attract water about the same as each other. But if we compare this to like sodium fluoride, which is going to measure basic, they don't attract water equivalently. Fluoride is very electronegative, much more so, and actually structures water around itself because of its dense negative charge very differently than sodium. And because it's so much stronger, it dominates, it wins out. And so now the solution is slightly more basic. But
So it's
if
like
you do
sucking, it's like grabbing up the free, oh, well, how does this work out? Yeah, what does that mean exactly that it's more electronegative in terms of what's happening to the atom?
Yeah, this is a great question. So what we're talking about with voltage is measured as like how much work it'll do on a charge. So you have like +1 or -1 electrical charge in an environment under a voltage. That voltage will cause that ion to move, right? Um, so usually when we're doing like, or a lot of times in physics, like charge work, there's a difference in charges, right? The issue is that water doesn't have a difference in charges. And this is a paper that Gerald Pollack has a paper on, actually. It's really interesting. And his conclusion is like a little bit different, but I think we agree. And it's that if you take the net charge of a beaker of water, it has no net charge. It has the same number of electrons as it does protons. So you don't get to do much chemical work or much electrical work because there's no charges like move around in this. There's no potential to move the charge, right? But now, what's curious about when you have a solution of potassium chloride, kind of have like the same thing. It's just like the same because there's no real difference between the potassium and chloride for water. But when you have potassium hydroxide or hydrogen chloride, this is a very strong base, potassium hydroxide, or a really strong acid, hydrochloric acid. So in this one, the small positive charge of the hydrogen in HCl attracts water way more dramatically than chloride ion does. So this is in essence why HCl adds the ability to do chemical work to water, because you have the same number of charges. I've not changed the number of electrons and protons in this glass of hydrochloric acid. It's equal. So the charge is equal, but it can still move charges. That's stored in it somewhere. And because the chloride is so weak in its attraction to water and the hydrogen is so strong in its attraction to water, and how it rearranges the hydrogen bond network around it is where you start to get these distortions, right? These like swirls in space-time that I'm talking about. Acids will always tend to destroy tetrahedral water. And tetrahedral water is the first time I've thrown this out here. And what that means is that water can get two hydrogen bond donors and give two hydrogen bond. Or it can receive two hydrogen bonds and it can give two hydrogen bonds. And so if you think like a puzzle piece, right? There's like two divots in and then two divots out to go connect to your nearby pieces. So if all four of those are connected nicely, this is perfectly like crystalline water. It's like ice, right? It's when you start to have like voids and rearrangements when water is like imbalanced is when diffusion happens. But so tetrahedral water is when all of these are occupied, and you can collapse tetrahedral water by doing something like acid. So acid H3O is usually how we talk about it. So I talked about like HCl, but the proton, the hydrogen in HCl, it doesn't just exist in water alone. It burrows into a water molecule, and this makes H3O, right? And so H3O has.
Let's take a pause here really quickly because I think that this is important. When we talk about acid-base chemistry, we almost always imagine that something that is acidic has these extra free protons that are floating around, right? The H plus. And when we think of something basic, we think that it has this hydroxide floating around, which is the OH minus. And so our mental model for what an acid versus a base looks like is the fact that there's just these loose, charged compounds, whether negative or positive, that are floating around that are screwing with the electrical condition of whatever substance that you put into that beaker. And what you're saying is really necessary to understand, which is that this hydronium, this H3O, is actually the conformation that the proton takes. It's not just like loose in water. It seems like it's strongly associated with a water molecule. And so it's still water that's doing this stuff. It's not.
And still a hydrogen.
Yeah. Hmm?
And still
It's
a
true.
hydrogen.
Which,
Yeah.
Yeah, but not loose. Like it's somehow like Michael said, like burrowing into the water molecule in a way where that's really different from the way that I always used to think about it when I was in school, which is just that there's this really activated hydrogen that's floating around totally loose in the world, as opposed to being attached to a larger molecule that's doing some kind of new work by virtue of its addition.
I like that because it's very disturbing to imagine a proton without an atom, right? It's weird how the chemists use the word proton, right? But proton's also the nucleus in a hydrogen. It gets very bizarre very fast.
And to return it briefly, because you talked about ATP synthase earlier.
Yeah.
And so I remember we interviewed Nick Lane, who does all of this like biochemistry and origin of life stuff. And he, as a throwaway sentence that I've never pursued, was like, it's really weird. The amount of protons, quote unquote, that we can find free in the mitochondrial inner membrane space is way lower than it should be for the reactions that are actually happening. And I think that this speaks to the fact that our perception of just loose protons out in biology doing stuff is really, really misleading. And so I just wanted to emphasize that because it's easy for somebody to get lost in, hydrogens, hydroniums, water molecules. I just wanted to give
Yeah.
like a
That's
Or
so
so,
helpful. Thank you. Go ahead, Charlotte.
oh, so can you retie that to the tetrahedral story that was
Yeah, so
emerging? Remind me
this,
what do you mean by tetrahedral water exactly?
so I'm kind of talking about how like for crystal structure lattice where like
So
carbon
like
or
ice,
diamond, ice and diamonds, they have perfect tetrahedral ordering.
both
So
called ice on the
every
street.
is that true?
Yeah, rock and ice. That's diamonds,
It
I
is
think.
fair.
I don't know. I haven't
Man,
listened
it's
to
deep.
enough.
I'm laughing because I scene switch, and so when Shiloh says something funny, I'm not ready for him to say it. He says it, and then the camera switches to him like a full second
Too
later.
late.
So I'm laughing because I'm like terrible at my job. Sorry, guys.
It's great. No, so the tetrahedral ordering in these crystal structures seems is at exactly like 109 degrees in four different directions apart from me. I can find my neighbors, and they'll always be at the exact same place. And so ice is this perfect crystal structure. And what's actually kind of interesting is that the water molecules, they can't translate around, they can't move like across from house to house, but they can actually rotate. They can change where their hydrogen bonds are directed. And so you can get like waves of hydrogen bond flipping in ice in a sense. So ice has got this tetrahedral breakdown. When you get a breakdown on that, you start to end up with liquid water. And liquid water is somewhere between this like tetrahedral ice network and something that's totally like fallen apart, where you lose all of that tetrahedralness. And where I start to connect this back to hydronium is that I talked about normal water being like this puzzle piece where you have like two acceptors of a piece and then kind of two donor lobes to hang out next to. So hydronium, because it's H3O, it is like having three donor pieces and only one acceptor. And this will like naturally distort the kind of puzzle pieces you need to like surround this with, right, in some way. And it's
And the way
actually a
that people
little
have thought about, can I just, sorry,
please
I'm just
do.
trying to catch up on this. So, donor acceptor, you're talking about the positive and negative regions of the water molecule, essentially.
Yeah,
Okay.
that's right. And maybe that was a good time to share some pictures. I'm not sure if that's helpful
Yeah,
or
let's
not.
do it.
We'll get to it then. Yeah. Um,
Pardon the interruption, but I have to ask you for a favor. We run this podcast without advertisements, without sponsors, solely under power of our patrons. And so if you have a couple dollars a month that you are willing to donate to a project that you think is valuable, come over to patreon.com/demystifysci. You can join us for our weekly patron chat, and in return, you get to keep enjoying the free content that we make twice a week for you. So hopefully we'll see you there at patreon.com/demystifysci.
maybe let's start off with the like water maybe being a mixture of tetrahedral and not tetrahedral. And skip
Perfect.
to some pictures. So I was just describing how ice has got this perfect tetrahedral ordering of water. And if we want to look ahead at a picture of what that ordering looks like, it's kind of just like this ordering here in this corner. So you have four neighbors, and so each water has the two hydrogens that it can donate, and then so there'll be a hydrogen bond to two nearby neighbors, and then two hydrogen bonds that it can accept from nearby neighbors. And what's curious is that ice, you have all of your hydrogen bonds satisfied, but liquid water is often described as a mixture of two liquids. And one of these liquids is nicely ordered tetrahedral water, where all of the hydrogen bonds are satisfied. And another version is where some of one of the hydrogen bonds is broken, and this causes kind of a collapse of the local structure. So uh, these are called respectively low density water for the expanded hydrogen bond version and high density water for the collapsed version. And what's really curious about this then is that when I start to talk about tetrahedral water, it kind of it directly starts to reference the shape where you have good hydrogen bonding. You have stabilized the hydrogen bonding between these partners, and they kind of make this shape or this network. And a curious thing about water being a mixture of these two is that because water can rotate and change its hydrogen bond to its neighbor much faster than it can translate through time and space, that you can actually, when you form low density water and it forms this increase in volume, it kind of exerts in a sense, it has to push out in the world around it, and the world around it's pushing it back in. So this is why it's kind of metastable, right? But the consequence is that you can transfer these pockets of low density water to other water molecules nearby faster than the water molecules themselves can move. So this can lead to interesting behavior like this shown in this simulation of Conway's game of life. So this is a common like physics toy model where whether the grid is black or white is depending upon the rules of its neighbors. And what's so interesting is that because of the way that water is, you could imagine that enzymes are these stable contraptions which can do these motions, passing things back and forth, and kind of send off like waves of tetrahedral or low density or organized water through the cytoplasm or through the liquid medium. And this is really, really potentially powerful for trying to imagine how this information travels faster than the fusion. So when I'm talking about these things in these bodies, these signals beating the actual molecules that make it up themselves, this is a nice mechanism by which tetrahedral water can kind of cooperatively move through solution in a coordinated way, and your body might actually be harnessing this so that when we start to synchronize systems, biological systems, if you zoom in close enough, something like this could be happening potentially.
And what's interesting, this ties to what you were talking about with the prions, right? But this is reversible, which is really interesting. So you have this infectious ability of these pockets to infect the next sort of more chaotically oriented waters, but then they take its place, it seems like, as the chaotic waters. Like you're still conserving the balance of tetrahedral water in this chain reaction.
That's exactly right. We're still conserving this, and this is so important because as soon as the tetrahedral water collapses, and it becomes that area where it'll suck in the next pocket of tetrahedral water. Right, it becomes ready to competent to receive the next thing. And so, as soon as you become tetrahedral water, you also become metastable. It's not there. You have to push out. And so the world pushing back in at you makes it so that you're going to want to collapse. So in this way, it's very cooperative, right? If your neighbor is strong, you're strong. If your neighbor is weak, you fall apart too, right? And this is in electron sharing through the hydrogen bonds, is how that force is like going to be mediated.
And the order, the time scale on this is really crazy, right? Because you're saying that the reformation of this hydrogen bond happens on the order of a picosecond, which is what, minus 10 to the minus 12?
I think 10 to the minus 12. Yeah, nanosecond 10 to the minus 9. So yeah, like if we're talking about milliseconds, right? My heart's beating on millisecond time scales. Microseconds, I have on this cartoon here, would be like conformational transitions of proteins. So that's actually going to be like enzymes like doing work, or maybe like a motor protein rearranging some. And then it has, go ahead.
And so all of a sudden what we basically have is, okay, so if it takes the water molecule a second to go from one end of the test tube to the other, then this is 12 orders of magnitude faster. You can get transport of information, not of water necessarily, but of information that the water is encountering across the same distance 12 orders of magnitude faster, which is insane.
It is insane. Can I clarify? Oh, go ahead.
I know one really interesting thing about this transference is that it's also a transfer of electricity or chemical properties, in the sense that this tetrahedral water has a different viscosity or a different oxidation state than the water around it. So you're transferring like information, but this information has a physical basis that can do chemical work as well. But Shiloh, you're asking something to clear up.
You made some statement about enzymes catalyzing the state of water. Were you making an analogy to enzymes, or are you saying that, because normally we think about enzymes as changing other proteins, right? Like sort of
or other molecules.
Other molecules, yeah, in general. Can you unpack that statement a little bit? I got a little confused by that.
Yeah. I should definitely qualify that more. So what I am alluding to is that what this model allows of this transfer of tetrahedral water is allows for interesting enzyme behavior to exist if we were to like look at it in this way. So now, am I insinuating that this happens? And the answer is there's a few places in biology where I think that this kind of thing could happen. And I think it'll happen in tissues that are synchronized. So if you take yeast and you delicately starve them, then release that starvation and add like some sugar, they will start to synchronize glycolysis. So what this means is that they're starved. Now suddenly they get a bunch of sugar, and they're all going to do the same parts of glycolysis together. So they're going to do like all these forward reactions, and then they're going to do all these backwards reactions, and all these forward reactions and backwards reactions. So you can image these yeast in a test tube, and you'll see them like flash with your probe reporting whatever you want to look at. So the concentration of NADH or ATP will all go up and then all go down collectively. The water degrees of freedom will go all up and then all down collectively. And
it's very hard to
yeah,
explain like that mob behavior otherwise.
it's really hard, right? And so this is the interesting thing, right? I would love to spend some time trying to like look into interesting ways to capture this. And there's a few biological systems that are out there, neurons being another one, or like muscle contraction, where there's intense cooperativity and cohesion of what this thing is doing, of what this cell is doing. And this is a mechanism by which you could start to understand how such a fast thing like beats diffusion in some other models. Right. And so this is the power of that. I think that this would exist if we were to look for it, but I don't think it's been rigorously proven yet. But there is examples that give us good evidence to think that this might be happening.
And with enzymes in general, I mean, what they're doing is oftentimes moving charge around. And I know that charge is like deeply nebulous, but if you look at how protein structures are understood inside their catalytic pockets, it's basically you get this map of the location of atoms, and if you're lucky, you've crystallized the enzyme with the molecule that it changes inside of its binding pocket. And people are like, oh, well, there's an oxygen here, and so when it and it's right near this bond, and so when the bond breaks, it must pass the electron to the oxygen that's there stabilizing the bond. It's basically assuming that the enzyme is absorbing the excess charge. But looking at this game of life picture, I'm like, whoa, what if it's diffusing it into the water too, right?
Yes. This is exactly where the pH story leads in biology, is that when you're having these waves of glycolysis and you're getting these waves of differences in pH and also water rotational freedom, you're literally like a flywheel, like offloading some chemical energy into the substrate and then pulling it back later when you do the opposite thing back. And what this looks like is that when you form ATP, actually, let's start off with breaking down ATP. So you have adenosine triphosphate. This means like adenosine is kind of a base that makes up our DNA, but we also use it as part of this molecule for energy, and then three phosphate groups. Whereas in your DNA backbone, it's normally just one. So stapling these three phosphate groups are negatively charged. So putting three negatively charged things together in this mini polymer is really like expensive. And this is where we think that we're storing our energy. Right. But when this ATP breaks down to ADP, adenosine diphosphate, and then this extra phosphate, so when the phosphates breaks off its tail, now you have to hydrate that phosphate. It has this intense surface area that has to be covered. So in a sense, you are changing the surface area of water that you have to cover with the salt. And this is going to change the pH, right? So when you start to rearrange these atoms, you do start to change, it manifests as a pH rearrangement. So you can offload energy from just the chemical, right? As opposed to storing it in the enzyme or somewhere. It can literally be stored in the hydration changes or energy difference of like the product versus the reactant, right? So then when you're having ATP and you're trying to rebuild it with ATP synthase, the most expensive part energetically is the last step of that. It's like it's a rotor with three stations. And so like the first station, you're going to get like ATP and phosphate and put it together in the pocket. Then the second station, as the acid flows out, is going to be to like force it into a bond. So you have ATP. And then the last station is going to be ejecting ATP out of it. And actually, the most energetically expensive part of that is the ejection process. And what this tells us is that oddly, it's very expensive to hydrate ATP. So when you have metabolism And these chemicals, they're having you're throwing charges around them. When you're throwing charges, you're also changing how strongly water binds that molecule. So there will be this balance that you have to have, where if you're going to do metabolism in a direction, you have to be able to hydrate those products. And at a certain point, you won't be able to. And this is why the glycolysis in yeast takes these like oscillations, right? At a certain point, you make these products and there's no more free water, or there's no more free whatever you need, and it starts to like unwind and it goes back the opposite way. So much like you're saying, and how you're like these enzymes are moving atoms around, and these atoms represent charge. Also, the hydration layer of those molecules represent charge as well.
So we're looking at
Right.
okay, sorry, I can't use that view. So what we're looking at right now on the screen is this I'm a little lost as to what's on the screen and how it connects
Yeah,
to what we're talking about.
so I think
But
what I'm
which I
trying
don't
to,
think is necessarily like, because I was thinking that I could probably just add it's like a video of the ATP synthase as it moves. I don't think that there's probably a video of one that's fully hydrated that shows this, but I know that like MIT Media Lab has done a bunch of simulations, which might be
yeah.
helpful for this. But the tie the biochemistry of what the ATP synthase is doing to pH. Does it tie to pH?
It does, and I may not be able to tie it perfectly because of I don't know enough about this system, but the ATP synthase for the mitochondria to work appropriately, it sets up a pH gradient, and as that pH gradient like unwinds itself, protons flow through the ATP synthase, and actually, so I'm not sure what I'm going to be showing here, but so if you can see my background, right? This is a piece of art I made about ATP synthetase.
A biochemist at heart, Michael Hughes.
It's all there is apparently. No, it's fun. I spent so much time trying to visualize these structures to make journal articles that I just got carried away with the visualization and like importing into 3D like modeling systems. But uh, you do have these like huge smokestacks, right? And so as the protons come up through the membrane, it will spin this this at the top part. And so this top part is where ATP, where it's not exactly where, but ATP is bound up. And then, so as it spins, it's going to actually move and shift and kind of push like ATP or ADP and phosphate together, and you're harnessing the pH difference inside and outside of a membrane, kind of like a hydroelectric dam. And then you're going to take that power and you're going to use it to basically, part of that gets end up as wrapping a sheet of water around ATP when it comes out ready made. That's basically what you're turning it into. And so I think that there's also, go ahead.
Oh, just we were kind of trashing the idea of free protons earlier. I was wondering if you think that there's a hydronium story going on behind the scenes with this ATP story that we've all heard many
I've
times.
always wondered about that too, because the conventional story is that the pore at the heart of the synthase is actually just a proton wide, right? Because there's a channel at the center of the protein where the hydrogens are supposed to fall down.
So waters can't go through it?
I don't remember this. Michael, do you remember
So
this?
Usually waters can't go through it from my understanding. And also the water channels, the aquaporins that we have, they are exquisitely and explicitly designed by nature, it seems, so that when the water is in the middle of the channel and it's going from the like extracellular to the intracellular, it's got to be tetrahedral water, which means you cannot transfer acid or base across an aquaporin because it has to select for exactly the water molecule, right? So aquaporins can let water molecules go in and out, but the structure will prevent an acid or a base from going in and out. Right? So you can have channels explicitly for this. And in fact, the channels that discriminate between sodium and potassium. So there's potassium on the inside of the body and sodium on the outside. The ion channels that are discriminating against this, it's really expensive to remove a water molecule from sodium because it likes water better than potassium. So the transporter actually transports sodium plus one water molecule, while potassium gets transported naked, right? So the waters that come along with these things and in these channels really matter.
And that's why sodium makes you bloat.
It holds on to water, yeah, in a sense.
That's
I mean, the
fascinating.
best I could come up with, but I'm not
So-
sure if I'd.
So you think there's free protons flying through these things?
Oh, hold on.
Okay.
I feel like this is a really interesting question. This is actually genuinely a super interesting question. But I worry that we've lost the thread a little bit. I have lost the thread. Have you lost the thread? Have we ever had the thread?
Well, I think we're looking at specific instances in biology where this structured transformation of water is playing out. And
Well,
so
like-
we've looked at a few, and we're kind of dancing
And so
around
with-
pH.
Anastasia was originally asking about hydration and the electrical part, and I was actually trying to.
Because we got to the point where we had the idea that an enzyme could be sending this sort of organizational pulse into the water that then gets distributed into the cell. And that's somewhat hypothetical. But we also got to the idea that pH was an arrangement of the water molecules, right? And so
Yes.
and we kind of have all these different pieces floating around where we have these enzymes that are catalyzing reactions, and the enzymes are proteins, and so the pH has to be appropriate in order for them to actually be able to do their reactions. And when the pH changes, what we're seeing is a change in the conformation of the water as it hydrates the protein, which then pushes it out of its native conformation, which prevents it from being able to actually do the work that it's supposed to do because it's not folded upright. And so is that relatively accurate so far, Michael?
Yeah, I think that's quite accurate. And yeah, would you have more?
Well, so what I was going to say is that if we leave the pH story there for now, which is, I think, a little bit clearer than where we started with pH for me, it seems like the logical place to go is exactly the slide that you have up right now, which is, okay, well, let's talk about electric charges in water. Because that's the next logic. If we've accepted that there's something about electrical charge and water and their interaction that creates pH, that's doing the work of the ATP synthase, that's being distributed through the cell to do work. Shiloh is smiling mysteriously. What are you going to say? What are you going to drop?
We'll get back to my proton pump later.
Well, I worry that that's...
It's okay if we can't answer that question. It is just always troubling me, though.
It is deeply troubling, and we should figure...
But yeah, let's keep the train on its tracks. It's fine. We'll leave that alone. I'm sure people are going to have ideas in the comments section.
I'm just... should we do that and then go to electrical
It's okay. I
charge
don't know the answer myself. I just I just have a hard time understanding the atomics of the situation with a free proton, or even contemplating what a free proton is.
There's a legitimate reason to be bothered by it, but this is a known feature of the ATP synthase, and so I feel like I can satisfy you in the background as we move to this question of, okay, pH is something about the way that these charged water species interact and screw with the ability of the vessel to do work. And so now let's figure out if we can understand electricity and water a little bit better, so that when we think about pH and electricity and proteins, we at least have some unified frame that the entire thing hangs on. Does that seem reasonable?
It's brilliant. Let's do it.
Excellent. So what I've like kind of covered so far is right, like what water alone looks like, and it's kind of this mix of tetrahedral and broken tetrahedral structure. And then if we put a surface next to it, this is where the origin of osmotic pressure kind of comes from, because the diffusion of water is now kind of messed up because one of the sides from which water could diffuse it to change its partners is now occluded. So this really slows down and changes how this water behaves. Now, electric charge basically comes from when we're talking about pH and salts dissolved in water. I think of it as if this was an average water molecule between two different, like two ions, and so one's positive charge and one's negative charge. Uh, how is this water pulled by these two ions? So one thing to keep in mind is that, again, the positive and negative charges are equal. The negative ion is going to be -1, the positive ion is going to be +1. But because they're different atoms, like lithium versus sodium versus potassium versus rubidium versus cesium, all of these atoms, they're +1 charge, but they're getting bigger as they go from lithium to cesium. So you're taking that one charge and you're distributing it over a bigger and a bigger surface area, which makes it weaker and weaker. So in this world, or in this case, lithium and sodium are really strong interactors of water. Water would rather hang out with these two guys than with itself. But potassium, rubidium, and cesium are the opposite. They're actually almost kind of slightly hydrophobic in a sense. The water would rather interact with itself than it would with potassium. And we care a lot about this because in biology, you have potassium inside the cell. So I'm about to unveil like why that's interesting. So in this, what I'm invoking here is that for two ions to come together, so when we're talking about metabolites being hydrated, I kind of like to think about when two molecules come together, uh, for them to come together like this positive and this negative, these gray circles, these waters, they have to leave for these two things to contact each other. So when you have like a super saturated solution of salt or sugar and you like hit it and it drops out of solution, uh, those molecules, they used to be covered in water, but now they're crystallized out of solution, they're touching each other, and it releases that water back into solution. And this actually restores the osmotic pressure, kind of, right? This is the balancing act of actual water molecules. So when you're doing metabolism and you're changing the surface area at the size, like going from ADP to ATP, or stapling a polymer together, you're really manipulating the osmotic pressure by the release of waters that are associated there. And this is kind of like one of the views. So now not only are you manipulating how many waters are covering you, you're also manipulating how strongly you're pulling on those waters. So here, if these was like lithium and a fluoride, the lithium pulls really hard on the positive, whereas the fluoride pulls really hard as a negative charge. And so as the two like kind of dissolve each other, you regain this water. And so in the cell, it's using negative charges like DNA or the carboxylic acids on our protein. So microtubules covered in very strong negative charges. Your RNA, DNA covered extremely strong negative charges, right? The phosphate backbone, phosphoric acid, very strongly acidic, very strong negative charges. And the positive charge that you have in your body is potassium, which is a pretty weak positive charge, right? So what's curious is that when you have a solution with two really strong charges, we call these cosmotropes, and weak charges chaotropes, they're not very soluble. So this is kind of saying that very strong charges really quickly get each other out of solution. So lithium is really strongly charged and fluoride is really strongly charged. So this salt is barely soluble in solution because it just water can't pay that much attention to the ions. But now when you get a really strong positive ion paired with a really weak negative ion, this is very, very soluble because the weak ion can never penetrate the hydration shell of the strong one. Because the strong ion is holding on, right? The lithium or the fluoride, it holds onto its water so tightly that a really weakly charged potassium or chloride can't like bounce in and push the others away, right? The water that's attracted to the lithium will never pay attention to that weak charge compared to another water molecule.
Really quickly, I just want to say that you have on screen these words cosmotrope and chaotrope, and I've heard them before, but I had to look them up. So cosmotrope is any substance that helps order water, and chaotrope is any substance that helps disorder water. And so when you're talking about the organization of the charges and their relative affinities and the end result of how things will behave in solution, you're also talking about how those charges are ordering water relative to their own preference for interaction. Is that a fair?
It's completely right. So the grand unveiling of this is that all positive charges will disorder tetrahedral water, and all negative charges will tend to order tetrahedral water. And the extent to which they do this, break down the order, or the negative charges construct that tetrahedral order, depends on how strongly charged they are. So very strongly charged negative things like fluoride or hydroxide tend to make a lot of like tetrahedrally ordered water. But then acids tend to break this down and make the kind of like it destroys the tetrahedral network. So when I'm saying that your pH then becomes a function of the strength, the difference of the strength of the charge, the negative versus the positive ion. So if there's a huge difference, then you have a big pH swing. So the most extreme incarnation of this pH swing, or a cosmotrope and a chaotrope pairing, is to have like the cosmotrope, which is in this sense like strongly ordering it's like sodium hydroxide, so the hydroxide ion paired with potassium, which has got like a weak positive. And so then hydrogen chloride is a really strong positive charge, which would be considered a cosmotrope, paired with a really weak negative charge called chlorine. So it's this imbalance that leads to pH. And I think that what I want to share about cosmotrope and chaotrope, I've heard these words before. I struggle to use them because they're actually quite poorly defined rigorously, right? Like it sounds really nice to read mixed order or deconstructs order, but how we actually like measure this makes it really nebulous. And so it's hard in just a like brief introduction. They're really good categories, right? Like this thing looks red, or this thing is about shoulder height, right? Like these are great categories to call a thing a cosmotrope or a chaotrope. But when we start to really dig into it, it gets just a little bit more complicated. Yeah. But
Okay, and so if I was to take the information that is on this slide, oh no, go back to the
okay.
slide. I still want to look at it. So you basically have two different conditions, which is that you're either going to get your compound into solution, or you're going to get your compound to precipitate out of solution.
Yes.
And so the way that this works is that, and it's not necessarily intuitive where you're like, okay, so if I add a molecule that orders water, it's always going to precipitate out. Or if I add a molecule that disorders water, it's always going to precipitate out. It seems more that if you add a compound that's made out of the same type of molecule, whether it's a cosmotrope or a chaotrope, whether it's something that tends to order water or tends to disorder water, you're going to get the same result, which is that those like substances with opposite charge, right? So charge here doesn't really influence whether it's ordering or disordering water. It has to do with like how tightly it can pull the waters to itself, right? So the reason that you have them in this kind of light outline as opposed to the dark outline is you're really talking about how is electronegative fair here? Like how good they are at structuring the water around them.
Right. And this will be manifested as a thing called like a polarized hydrogen bond. So if you're water and you're hydrogen bonded with water, it's the same. There's not necessarily polarization between you because there's no like massive difference in charge. But if you're water and you're next to like fluorine, which is really left or negative on one side, that fluorine is like kind of in a sense that negative charge is pushing your electrons away from itself, right? And so this is actually going to polarize because now the fluorine is pushing the electrons more into the oxygen. Then it's going to actually now become like a better acceptor of the next hydrogen bonded water out in that chain because the fluorine like makes that charge difference greater, right? And so this is where this cooperativity of hydrogen bonding comes in because if you're hydrogen bond, if you're water and you have a polarized hydrogen bond with something really strong nearby, you're less likely to leave, right? You don't get you're at a more stable energy configuration right there with that really strong hydrogen bond, polarized hydrogen bond. Yeah, so acids and bases are extreme polarizations towards the positive or the negative charge and the oxygen or the hydrogen in water.
And they're not things that are not polarized, basically, right? Because like in both of these conditions, you're like, if you have something that's really too a positive and a negative charge that are both equivalently like attractive, that they're not going to interact with the water, they're going to interact solely with themselves. So you kind of need this imbalance within the molecule in order to actually get to the point where it's able to affect the water structure, because you need it to interact preferentially with the water rather than preferentially with itself.
Exactly, right. And so our body uses a very particular ordering, right? Because it employs this like ramp in a really particular way. And what it is kind of like pairing the opposites with each other. So the negative charges in our body are really strong negative charge cosmotropes. So they really like to water and to polarize these hydrogen bonds. And so DNA, RNA, they have phosphates with these negative charges. And then in proteins, the glutamate and aspartic acids, these are also cosmotropes. So all the negative charges in our body are these. Whereas for the positive charges in our body that we normally have inside the cell are potassium. And this is one of those chaotropes, right? So this keeps everything really, really soluble, but also really, really soluble where we can put all of that crazy amount of protein into this really concentrated mixture and not have it unfold, right? Not have it crash out in that amyloid disease. Because we're pairing we're really harnessing the ion or the salt pairing to incentivize everything being soluble and in solution. So
Can I ask a question about potassium? So potassium's gotten a lot of play in the medical health circles recently. Like, I think I saw the stat that between 60 and 80% of Americans are potassium deficient. I assume that the cell maintains its potassium concentrations rigorously, even under cases of deficiency. So what is the stress on the body when we don't have enough potassium in our diets?
I don't know if I can answer that yet, but I would love to, because the thing I do know about that is like what's really curious is that this gets into what a biochemist by the name of Gilbert Ling proposes, because Gilbert Ling is kind of infamous in biochemistry circles for thinking that the sodium potassium pump doesn't exist. But we've handed out like Nobel Prizes for the structures of this, and people have very rigorously figured out that something that looks a lot like a sodium potassium pump exists. Right. But what Gilbert Ling is basing his observations are, and the really remarkable thing that he's looking at is that if I take muscle and tissue and I like cut off one end and then put that in a salt solution, we would expect like ions and small molecules to be able to dissolve into that muscle, right? And so then you can kind of measure how quickly those ions dissolve into that muscle as it travels up from the beaker, if that makes sense. And what Gilbert Ling finds is that muscle cells, they can absorb tons of potassium and cesium, right? If you just put it up there, it'll pretty freely diffuse into the cell. But if you put the muscle cell into a sodium chloride solution, the sodium does not enter very quickly at all. The sodium is actually like excluded from the cell, right? So when we're talking about like pumps or maintaining homeostasis, there is one view in biochemistry that I think that is commonly taught from metabolism based point, is that we're always like pumping things out to maintain this like steady state. And what Gilbert Ling is trying to reveal is that even without any input of energy, we got this muscle cell off of a dead frog. That there's no like active maintenance. It still actively maintains its hydration environment and does not let sodium in without like hardly any energy expenditure, right? So it's passive. Right. So what I'm trying to open up here is a weirder way of which we can do work that's much more efficient than what we expect normally. Because as opposed to just spending the energy to go somewhere, we're harnessing from a work cycle. And so we can like put it somewhere and then drop back out potentially.
And yeah, so can you say more about how the cell would use the water to exclude the sodium, building off the concepts we've been talking about?
So because of sodium really needs that hydrating water, and it seems like the intracellular water, it seems to be again like in the cytoplasm, this seems to be the case, but in the nucleus, it's very different in the sense of it it seems to be more tetrahedral in the sense where if you have it seems the tetrahedral network of water is incompatible with the sodium ion's desired hydration because the sodium ion tends to destroy tetrahedral water because it's more charge dense. That's its nature. Whereas potassium tends to enhance and support that tetrahedral network. So what the argument is that the tetrahedral ordering of water that's kind of enforced by the somewhat negative charge bias, the presence of potassium, and also the incredible like surface area structuring of colloids of different tiny particles in water, meaning proteins of their surface structuring the water tends to make it in this tetrahedral fashion, and this kind of pays the energy for it to be incompatible with sodium. So sodium just doesn't like to dissolve into there because it can't go into the hydration layer. It's not very good at it. Uh, Except there are some situations where our body does make it very good at this. And neurons are a rare thing where it seems that like sodium just enters into a neuron, but this doesn't happen spontaneously in a muscle cell, right? So this is really interesting. Also curious, a neuron cell is almost like 97% water, whereas a muscle cell is very far from that, right? It's like steak.
And
So,
it's got calcium in there as well. That's playing a really important
so
role, which is another one of these
yeah,
chaotropes. Hey,
cosmotropes actually. So the punchline of when so our bodies are normally keeping really strong cosmotropes as negative charges, meaning our DNA and proteins inside, and then a weak chaotrope, potassium is balancing the charge, and that's really soluble. But when we want to do action, meaning like contract a muscle or send a neuronal impulse, both muscle contraction and neuronal impulse, a muscle contraction uses calcium and neuronal impulses use sodium. So in calcium, because it's +2 charge and it's quite small, holds onto water very tightly. And so because calcium is a cosmotrope and the binding sites on actin and myosin, the protein cytoskeleton filaments, are also strong negative cosmotropes, they like to it then precipitates onto the muscle fiber, right? The protein fiber. So this is then going to be what the work cycle is, right? It's going to look like this ion precipitating, releasing that hydration code. That hydration code then changing the osmotic pressure, and therefore you get some mechanical motion and you get some change, and then it's going to reset this state. So this is like the world that Gilbert Ling then builds out and sets the stage for, is trying to understand these mechanical work cycles that our cells go as this electrochemical exchange of ions. And there's a very particular gradation of which ions bind where. It's very like understandable. And then we can kind of see where this excess volume or where weird osmotic pressure effects can come from related to the pH from this and the charge. Yeah.
That's super fascinating. And I love that it creates a really material way of thinking about this. Like the atoms have properties, and their properties are related to their size. I mean, charge is a little bit nibbly wibbly because it's like at the end of the day, like what exactly is charge? We're still stuck with that, but they do have more or less of this property.
Certainly seems to be, at least I think we can all agree that it seems to be something that the atoms are doing to each other.
Absolutely.
And that's a
And they
good
have
place to
more or
start.
less of that ability depending on how big they are and how tightly they hold this.
How that action is spread out over their surface and so forth. Yeah.
It's almost as if you spend a lot of time thinking
It's
about these sorts
almost
of
as if,
questions.
yeah. But I think that's a non-controversial perspective that's beginning to emerge.
But I love the idea that these things are all related to one another, and it's not just these ions that are doing stuff, but it's the ions in context of the relationship of the cell that is allowing them to perform the actions, which is, I think, a much more entangled way of looking at biology,
Yes.
as opposed to like water just kind of being there and we're like mostly water, but
Right.
surely that's just incidental because it's a really good solvent.
Right. And so what's cool about this with this kind of I guess economy of the electricity and how it moves through the body in these work cycles is now is like a lot less mystery in where we would search for answers for disease, right? It's a lot it's much easier to understand what the proper work cycle and like why it would look like this. And so when you start to get issues with like solubility, like Alzheimer's disease, these kinds of things, we can go from worrying about random events in your life that will nucleate just this random ice crystal that you now have this prion disease to something where you are experiencing a biochemical environment in your body which changes the solubility of normally soluble things. And this actually explains everything, right? If you're a cell carrying out a genetic pathway, this involves proteins binding to DNA at the right place and time to then execute, right, like copying that gene or turning it into a protein, whichever way. So the very action of that protein binding to the DNA, this is an electrical event, as I'm kind of talking about, right? There is like a transaction of that protein is charged, the DNA is charged, and for it to come off, it has to be hydrated, not only by water, but also by counter ions, the equivalent counter ion. And so when we think of like equivalent counter ions, ATP is the main equivalent counter ion in the cell. So we normally think of ATP as this energy source that we're consuming. But what I'm actually trying to reframe it as is more of a detergent that keeps things soluble, right? It's this really strong cosmotrope negative charge. And so it has some really interesting hydration properties that we don't necessarily expect. Almost every protein or molecule you put into solution tends to slow water motions down around it, right? As you're like paying attention to this thing, it slows you down. ATP actually has a hydration coat of kind of like agitated waters. It's like waters that really want to change their bonding direction. So ATP dramatically changes the hydration properties of the cell, and that when you start changing hydration properties, this is looking at like a transfer from cancer or from a normal cell to a cancerous cell or from a stem cell to a normal cell. This is all going to be a dehydration or a rehydration reaction to get those proteins on or off the DNA according to this.
I was really tempted to explore the idea about consciousness because people are very comfortable thinking of the brain as working through this patterned electrical circuitry. And all of a sudden we have patterned electrical circuitry appearing in the water structures themselves. But one thing that's really different is that this seems to persist even after the organism is dead, which is really like, it throws a wrench in my idea that there's some extended computation that is a hallmark of life going on inside of this water. Because
what does that extended computation look like to you? Or what are some aspects of it?
Well, it seems like there's information and memory that are locked into this patterned organization of water. If we've agreed that something can happen in one cell and then pass that signal along to a cell that's far away, then what we're really talking about in some ways is this like soluble nervous system. I mean, like obviously it's not a nervous system because
that's
it's not
my
neurons
intuition.
or whatever.
Yeah.
But it does seem that way, right? Because like as far as I can tell, there's not a separation of the compartments of water in your body, right? So there's exchange between blood vessels, between cells. There's aquaporins. There's junctions that allow for there to be a continuous flow of molecules throughout the entire body, right?
Yes. And the consciousness, there's two ways it can go. The consciousness one, or there's this really interesting thing with the flow of water, which I think is like cool to hit, and then maybe the consciousness. But this is the school of thought that I kind of like leaving off at. I'm trying to write and wrap up the ideas that I've shared is, osmotic pressure and pH as a function of these really small scale motions. But there's some very, very exotic like theories on biology and biochemistry as we zoom back out about this like flow of water in an organism. And one of the ones that's most captivating to me is put like there's a few ideas. One is put by I think Professor Laszlo from UCLA, and he kind of did this back of the envelope computation where he looked at about we know how many ATP synthetases there are on in the mitochondria about, and we kind of have this idea of how many mitochondria are in this amount of like tissue, and so you can like weigh a person and then kind of do the math for how many protons would flow through this ATP synthase in a day. So how many protons are flowing through this person in a day? And the answer is that about enough protons for about 2,000 gallons of water are processed every day flowing through your ATP synthetase. And what is also curious, if you do another back of the envelope calculation, the average person's like blood flow, right? About how much you think that the heart pumps a day is about 2,000 gallons. And so this like links up kind of like suspiciously nicely, but there's a lot of like play in these things here. The third thing is this biochemical idea that the heart is not a pump. And this seems extreme because I'm trying to like be an employed scientist at the end of the day.
This is true. This is so like I think that it's important to remember that as an employed scientist, you're only allowed to have one extreme idea at a time. And
Right.
at that, probably like only one extreme idea per decade. And so we'll set this aside as we'll put an asterisk on it mentally. But
Right.
I just went to this conference, the renewal of science, and there was a guy there whose name I think it was Branco. He was an anesthesiologist in New York State, and he made the case that it wasn't a pump. And I've heard this before, and I was just kind of like, yeah, like okay, I'll listen to it. But he actually had clinical examples of people who, like, they weren't very healthy, like, let's establish that, but they had blood flowing through their bodies and their hearts were no longer pumping.
Yeah.
And so that, to me, is like, it might be acting as a pump in some cases, or it might be pumping, but the fact that you can have blood flow, have somebody be alive and moving and, yes, sick, but still functional without the heart actually performing its normal contractile motion, that to me was evidence enough. He had like CT scan or like ultrasounds of the blood,
Right.
and you could see the not an anatomist. What are the flaps called? The valves?
Yeah, the valves is, yeah.
The barn doors.
The barn doors in the heart. You could see them opening and closing, so you could see that the blood was moving, but the ventricle was not contracting. And so
Yeah.
whatever, I've emailed him, I'm hoping he comes, but whatever it is that you're pointing to
Yeah.
is out there.
So yeah, this is out there, and that's what's so important about this like water story is that the flow of blood in your body comes from somewhere. It's unclear if it's your heart, but this would be a place to look. Is this metabolism of your body just like being this kind of breaking apart and reforming water as this like vortex is then what's pumping is right. So that's why the volumes are the same.
It just occurred to me that this entire conference was deeply centered around Rudolf Steiner.
Yeah, so
And
this is the line of thought that people often reference Steiner in their scientific papers in introducing this because you should share how you came across it. Yeah.
Well, no, I realized that it's something that you'd be interested in because I know that you have this affection for
That's right.
Steiner. And it was
I heard this years ago. I was listening to one of his things like 2 years ago, and I was personally listening to Steiner, and it was like, man, I guess he's off his rocker today, but tomorrow I'll tune in and see what's back. And then 2 years later, it just becomes a lot more like convincing. So he was effectively saying in 1910s, 1920s, he was giving his lectures to physicians saying, if you're to spiritually understand, like doctors need to get around this concept that the heart is not a pump and that this is an incredible error in how we're treating people. And this will lead to complete dismay in understanding the body and how it works because we don't understand where blood flow comes from. And so when you're trying to treat the blood flow issue as a heart pump issue, you're not actually treating the blood flow issue if in case it does actually come from like water metabolism, right? So we might want to care about this. I'm not saying it's true or not, it's too early to say, but there's some interesting tie-ins that connect these ideas in a very serious way.
The heart does appear to be pumping, though.
The
right?
heart, it does pump.
It's doing a pumping action.
It pumps, but it appears to not be necessary for the blood to move, which is what's crazy. Because this is the thing. In biology, we have a thing of like necessary and sufficient. And so it appears it appears to not be necessary for the heart to pump for the blood to move, which is crazy. Because usually when you're making the case that this molecule that you're looking at is responsible for the effect, you're saying that not only is it sufficient to have the molecule there to see the effect, it is also necessary to have it. And so all of genetic molecular experimentation is done on the basis of this, that you have a mouse model where you take out the molecule, it doesn't make the protein, the system breaks.
I mean, surely the person's not doing too well if their heart's not beating.
They're definitely sick, but their blood is still moving through the body without the heart pumping.
How long does this last for?
There's another observation where one of the things often cited in this line of work is that an embryo, if you're looking at embryonic development, the blood will start flowing before the heart develops, right? There's some ways you could like work around this by...
I guess through the mother or something.
The arteries also have musculature, right? Arteries have smooth muscle and like veins don't or something. Like there's some things where you could like find some motive force somewhere else that's musculature. But there's a few modes where you get blood flow without uh, a pump, right, without the heart being functional. And so when I'm like earlier showing the Conway's game of life, where you can have like a protein like going or an enzyme going back and forth, and you get these like pockets of water going out. What's really important for the Conway's game of life work is that there's like an outlet for that like built up pressure, right? And so whenever you're doing a chemical reaction one direction, there needs to be something going out somewhere. So what this is saying is that if you have an idealized physical system of just a piston, like a cylinder that's like tracking and expanding, if you're just looking at the piston like getting bigger in space and you don't take into account how this piston moves into this other environment, it moves into some other area. There's a countercurrent. And this is an idea explored by Professor Robert Eisenberg, I believe, where in electrochemistry, there's Kirchhoff's laws. There's two laws. There's one on gas, and then there's one on, I think, circuits. And I think that Robert Eisenberg's premise is that most electrical engineers forget about this like return circuit that he has built into his original formulation equations. They use a different set of equations that kind of like simplify this. But in the original implementation is that there's no way to get like forward motion without a reverse motion allowed, right? So there's no way to get current somewhere here without another current coming back this way, right? So this heart flow is really important because if I'm saying metabolism goes in a forward direction, you need a place for the current to go to and a place for it to come from. So when you have these salts going like backwards and forwards, right? The calcium binding to the protein or fibers in the musculature and then being like adsorbed back into the body somewhere. You always have to have, whenever something's going somewhere, there's an equivalent pressure release somewhere else that lets it move to there. And if we don't account for this in biology, we'll be lost to, or physics in general, right? And so Kirchhoff calls this the countercurrent, I think.
What do you think, Charlotte?
I think that you had a surprise saved for us.
And it ties nicely back to this idea of ATP and the ATP. Is it synthase or synthetase?
I grew up calling it synthetase, but whenever I write it out, it seems like it's synthase. But yeah, I'll trust you with whatever you throw at me.
I thought that, okay, the thing that makes ATP inside the mitochondria, we were talking earlier where it's the model is that you have this electrical dam where you have protons on one side of the membrane that are put up there by the electron transport chain, and then they fall down this pore that's at the center of the ATP synthase, which then regenerates ATP by screwing a phosphate onto the end of this depleted molecule, which just has two phosphates on it.
Screw those phosphates.
Screw those phosphates on. Yeah, exactly. And then it goes out. And I love what you said about the idea that it's not fuel that's burned. Like, I think that this has been floating around in biochemistry for a long time, where we have this way of being like, well, it's ATP is fuel, it's being burned, it's being consumed or something like that. But people are starting to realize that there's something else that's happening in the process of removing the phosphate molecule. But in the process of adding the phosphate molecule, they've made crystal structures of this F1, F0 ATP synthase. And they have the pore size, which is thought to be the pore through which the protons must travel. The pore size is about 3 angstroms wide. A water molecule is about 2.7 angstroms.
Yeah.
A hydrogen atom is 1 angstrom, and a proton is like 10 to the minus 15 angstroms.
Yeah.
No, sorry, 10 to the minus 5 angstroms. And so from a completely like idiot surface read, it seems impossible that what's falling down that pore is a naked proton, because you need the entire
alone.
Yeah, like a naked, what I mean, like
only a naked proton.
Yeah, only a naked proton, because in order for the pump to work, to be able to screw the phosphate back on, it's a ratchet. And the idea is that like one of the protons falls into place and then switches its motion. And so you can't have a pore that's 5 orders of magnitude too big, because then you wouldn't have this exchange of 1 proton per 1 ratchet, which is what you're supposed to have.
You're keeping my hope alive. There's a rational explanation for this thing at the end of the day.
So, it's got to be something else.
Ling did a ton of work on my favorite idea by his that I didn't like touch on today, but is really undervalued, right? Like if I was talking to biochemists and I was talking to a room full of biochemists, and it's like one thing that I think is important that everyone should go home with. It's completely this idea from Ling called the association induction hypothesis. And what it's saying is that if you have we'll talk about ATP binding. So ATP is negatively charged. It's going to bind something that's positively charged. And so uh, normally when those side chains on that protein are just positively charged and hanging out there, that positive charge is actually attracting electrons from the protein backbone, the polypeptide chain, to like hang out closer to that positive charge. Whenever you put that ATP there, now you push those electrons because that negative charge, first of all, you cancel out the positive charge, so it's not pulling the electrons anymore. But then not only do you cancel it out, you also have this huge negatively charged ATP there. And this pushes the electrons into the protein backbone very slightly. But this is going to be where that charge transfer you're looking for, that's going to be really nebulous in these weird charge transfer things, is because when you actually bind a charged salt to a protein, it's going to change the molecular motions that that protein experiences because of pushing the electron density away from that like ATP and into somewhere else in the protein. So you get to the cooperative charge transfer. So and now you can like add this up in like microtubules, right? Like if I bind something charged here, because of that pushing of the electrons, something can happen very far away because it's just like a slight change, right? Of that carried on down the line. So you can get weird transfers and that might look like this with charges. Yeah.
That's super interesting. I mean, it's impossible to get to the bottom of all of this over the course of a single conversation, but I think that
Yeah.
I'm immediately struck by all of the different ways where it could go. Shiloh's thing about consciousness, I think, is really interesting, and the structure of the water maintaining some kind of information, some kind of memory, and how
One of
that
my
actually.
favorite. Yeah. The reason why your neurons, the hydration environment of your neurons are very, very, very unique from what it seems. And it's like maybe a story for a different day, right? But these are very specialized cells defined by being extremely electrically active. And what's weird about them is how water rich they are. Your neurons are completely filled with water. And this originally struck me as odd because Rudolf Steiner described the feeling of neurons as cells that are almost dead, right? And I didn't quite get this because I thought that neurons were really, I always compared them to muscle cells because they're both really electrically active. But the difference of a muscle cell is it's very not hydrated, it's just filled with protein, right? And so this world where neurons inhabit, very filled with water, allows for really, really interesting interactions with light in particular as a way that can transfer momentum into those water molecules. And I think that this is where like the consciousness thing comes in. And it's like a story for a different day, but it's one that I love and one that this like really alludes to when you like get the groundwork. Yeah, yeah.
Yeah,
That's
bringing
fantastic.
light into this picture would be a whole nother level, right? But
Yeah,
I think we
yeah.
have to save
It's
that.
a different day. Yeah, that's where the consciousness I think goes for this kind of system in biology. Yeah.
Do you think that we've done a decent job of laying out the big picture that you're aiming for?
Yeah, I do, and I'm so thankful for you guys like helping me talk through this. I think it's a real struggle to I mean uh find people to chat to about this and kind of process these ideas, right? It's like me sitting here alone. So to be able to have this exercise and kind of like lay it down and get these ideas thrown back at me is really helpful. Thank you very much for hearing this out. I think that I got to get a lot of the really cool ideas that I came across and how they play into biology, which is probably where I care about the most.
What's next for you? Trying to write this up or do some more simulations or what's next?
Yeah, trying to figure out. I'm writing up this general outline of this kind of like hypothesis I put together of a more like water-centric way of accounting for action in the body or physiology and cell behavior. And I think that this is going to be a pretty surface level article, which is nice because it should be very like approachable and readable. Uh, I think that at some point in the coming years, I'm hoping to really like rigorize a lot of the stuff I shared. I have, hundreds of sources to cite, but that's very boring to average people. But it's that thing I probably have to like rigorously lay out over some time. And so as soon as I get this published, I'm probably trying to look to apply to next job. If yeah, anyone that's interested in water research, I've got some ideas I'd like to test. I think I've developed a lot of like testable hypotheses, and I would love to experimentally test them and it'd be trying to look to connect with people in situations that would let me do that for sure.
Hell yeah. That's gonna be really awesome. I
think so.
I don't know. It's really cool stuff, man. I appreciate you. I really
Thank you
appreciate
so much for listening.
spending the time to dive into it and spending the time to talk to us. And I think that our audience really enjoys it too. And let's do it again in a little while.
That sounds great. Again, yeah, it's this crazy deluge of information. It's hard to turn into a storyline, but it's so helpful to go through these exercises and chat it through. Thank you very much for having me on and going through this with me.
Yeah.
Yeah, I think it's shaping up. It's structuring.
It's structuring perfect. It was there all along.
All right, Michael. That's awesome.
Excellent.
It's always awesome to hang out with you. So we'll see you again soon, man.
Likewise.
Yeah.
See you guys soon.
Bye, everybody.
Bye.
Yeah.
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 Thanks, guys.
Yeah, man.
Appreciate
Yeah.
it.
It's
Great.
I'm always intimidated by this subject, but it's I feel like I understand it better now. So I need to go and digest all these thoughts.
I'm glad that I think that's what was most interesting to me was like it's so nebulous, it's so vast, but it makes more sense. And it's hard for me to understand what the story that I tell someone is that quickly gets them to where I am without like scatterbrain all over the web. Because I do think it helps like my intuition, right? My intuition is so fast for biochemistry now in a way that I never had my entire career, right? Because I just know what these things are doing, what they want now. Right. Those weird things that I find out about water, they're again, what's weird is like there's just mechanism. It's no longer weird, right? I just know exactly if every weird water fact that someone throws at me, like where I would look for that. And I wish to get that out as best as I can. And so that's what, yeah, I think
I think
nice
we
to have
took
this
a pretty
kind of
good bite out of the
circle.
apple today. Like I
We
think
did great.
I feel like I
It's
can
really
visualize
strong.
it better now than ever before. So that's good. I think other
Yeah.
people feel the same way. But I'm sure I'll have more questions
Yeah.
soon too.
And it's just going to be really cool to see you as you spend more time developing how to tell the story and finding new because the experimental thing for me is really exciting because I feel like as soon as you start to go from theory to demonstration, you've hit the next level of like, oh my God, not only is this just theoretically accurate, we can show it and then we can actually do stuff with it. And it just opens up this entire door of possibility for something that the world really needs because even the way that you're talking about, cancer and Alzheimer's and all of these metabolic disorders, if this is the path to solving it,
Yeah.
that's incredible because it's in plain sight. You have an intuition
Right. That's what
for
I'm
it.
hoping.
And so
Yeah.
it's like, fuck yeah, change the world, man.
Yeah. Just hoping to share that intuition. It's like all I got, but I hope it's like enough and interesting. Yeah.
Yeah,
Thanks so much for the help. Yeah.
it's gonna be
All right,
really good.
cool. Yeah. I'm hoping to catch you guys there, and I'll definitely send whenever I have something cool, like a draft. It should be like pretty approachable. I'll send it to you guys. I'm looking to spend a month illustrating it because I love the illustration. So I'm trying to like go pretty wild on the picture book side of it, and I'm hoping that's like a nice experience for people to like really be approachable. But I show this out there because I mean, I'm looking to connect with people like you, like enthusiasts who are interested, who don't have all the like, I have way too much information in my head. I can't judge what I'm saying. So anything you guys throw back at me is really helpful for what works and what doesn't.
I'm sure we'll get some good feedback from the audience too, and the other patrons and everything.
Yeah.
So
Yeah, definitely.
yeah, it'll be really good.
Same. All right,
Yeah,
cool.
good work, man.
All right.
Okay.
All right, have a good
Thanks.
day.
I'll catch you guys
Rest
later.
of your day.
Bye.